So we're going to take a look at chapter 9. We're looking specifically at the concept of probability. And in the first section, we are going to break it down by looking at how probabilities are determined, looking at empirical probability, or what I like to refer to as real world probability versus theoretical probability. So in theory, we should flip heads out of tails 50% of the time, but in practice, we may not actually see that. So that would be experimental versus theoretical probability. We're going to look at the properties of it. We're going to look at mutually exclusive and non-mutually exclusive events. And then we're going to take a brief look at geometric probabilities. So first, let's define an experiment. An experiment is any activity whose results can be observed and recorded. So just flipping a coin, if you write down your results, is considered an experiment. An outcome would be each of the possible results of an experiment. So if I have that coin, my outcomes would be heads and tails. A sample space would be this set of all possible outcomes for an experiment. So whereas I could say a heads is an outcome, if I wanted the sample space, I would say heads, comma, tails, and I would use set notation for the brackets, which you'll see. An event is any subset of the sample space. So if I flip the coin and I get heads, that is an event. It's a subset. So let's look at an example. And this is when we get into the examples, these are the types of things that you might see in the lab. So suppose an experiment consists of drawing one slip of paper from a jar that has 12 total slips, each with a different month of the year. Find the following, the sample space. Well, if each slip of paper has a different month of the year, then my sample space, and notice how this is noted, S, capital, equals, and I've got those nice squiggly brackets, and then I have going on from there, January, February, March, April, May. So that's listing out all the possible things that I could choose. That's my sample space. The event A consisting of outcomes having a month beginning J. So then I'm going to look at, well, there's January, June, and July from my sample space. Since it's a subset, it's going to be considered a event. And I'm going to utilize A because it says capital A. Event B would be the name of the month that has exactly 4 letters. So I'm going to my sample space and finding how many have 4 letters and putting that in set notation. Then if I want an event C that consists of outcomes having a month that begins with M or N, that would be March, May, and November. So the difference here is this was all in theory. I wasn't actually drawing the slips of paper. Now we're going to look at experimental probability, which is going to be observing the outcome of an actual experiment, whereas theoretical would be under the most ideal conditions. So when you flip a coin, there's things that are in play like friction, air friction. There's a slightly heavier weighted side of a coin. Those kind of things can affect the outcome. So that's why we say theoretical. If something is equally likely, then it means one outcome is as likely as another. And a uniform sample space means each possible outcome is equally likely. So what we say is we have this law of large numbers because if you've ever flipped a coin, you might have noticed if you got heads the first time, that doesn't imply you'll get tails the next time. So that if you had 2 flips, you had exactly half of your flips heads, half of your flips tails. What the law of large numbers, or Bernoulli's theorem, says that if I keep flipping that coin, the number of times that the experiment increases, so say instead of flipping it twice, I flip it 2,000 times, that the experimental probability will approach the theoretical probability. So if I flip my coin, let's just say 2,000 times, and I recorded each time heads and tails occurred, because that's such a large number, I should see really close to 50-50. So 50% should be heads, 50% should be tails. I mean, it's not going to be exact, but we should be moving into that ballpark because we're doing a large number of experiments. So the probability of an event with equally likely outcomes, so heads and tails, equally likely, would be the number of elements in set A, which we're going to define as the probability of some event happening. So if I say, what is the probability of flipping heads? That would be 1. So the numerator would be 1 because there's only 1 heads in my sample space. Then it says the number of elements in the sample space. So the sample space for a coin is heads and tails, meaning there are 2 events. So it's 1/2. Here's a different way to think about this. I like to think of it as the number of desired outcomes divided by the number of all possible outcomes. That's a great way to think about it. So let's look at an example. If I have this sample space, if a number is chosen at random, that means the same chance of being drawn as all the other numbers in the set. Calculate the following probabilities. I want to look at the number of times the even number is drawn. Well, how many even numbers are in the set? You're going to count up the number of even numbers, which would be 12. Then you're going to count up the total amount in the set, which is 25 because it's 25 numbers. And my probability is my desired outcome of an even number divided by my total outcome. So 12 over 25, which in the lab could also be asked to be written as a percent. Pay attention to those directions. In event B, if I want a number that is less than 10, now less than 10 means not including 10, and greater than 20 is drawn. So there's no possible way to draw a number that is less than 10 and greater than 20. So it's 0. The probability is 0. What you have to be careful of is this question does come up in the lab where there's an impossible task given, and you have to recognize that it's going to be 0. So just stay on the lookout for that because it can be a little bit tricky. We want the probability that a number less than 26 is drawn. Well, there are 25 numbers that fit that criteria, divided by 25 total numbers, which would be 100% or 1. If I want to look at that a prime number is drawn, I'm going to have to go back and look and say, what's a prime number? Well, prime numbers are numbers that are divisible by themselves and one other number. So if I look at from 0 to 25, the prime numbers are listed here, and there's 9 of them. So the probability that I'm going to draw a prime number would be 9 over 25, because I desire a prime number. There's 9 ways to get it, and there's 25 total outcomes. If I want to look at the probability that an event E is both even and prime, I'm going to look at it and say, well, the only number in that list above that's even and prime is 2. So I have a set element of 1 over 25, and that's my probability. And a possible event is an event with no outcomes, which has a probability of 0, like we just saw. A certain event is a category of an event when we have a probability of 1 or 100%, like we also saw with the question asking for how many ways can we draw something that's less than 26. If A is any event and S is in the sample space, then the probability has to be between 0 and 1. If you're getting a number less than 0 or greater than 1, you've done something incorrectly. So the probability is going to be equal to the sum of the disjoint probabilities. So what does that look like? Well, let's say we've got an ordinary deck of cards. So first, let's review what our deck of cards looks like, because sometimes we don't play with cards as much anymore. A deck of cards has 52 cards. It has 4 suits. It has hearts and diamonds that are red. It has spades and clubs that are black. And each suit has 13 cards in a suit. Our face cards are king, queen, jack. And then we also have the ace in every suit. So if I want to know the probability that I draw a card and it's an ace, there's 52 cards, like we said. There's 4 aces, 1 for each suit. So it would be 4 over 52, which reduces to 1 over 13. Now, if I say an ace or a queen, so this is what's different here. I'm doing 2 things, ace or a queen. So what that's saying is that I'm going to add the number of aces, which are 4, to the number of queens, which are 4, to get 8 over 52, which reduces to 2 over 13. So it's not 2 separate events in the idea of I'm drawing 2 cards. I'm drawing 1 card, but now I can have 2 outcomes with an or statement, and that's why I add the aces to the queens. So it's not 2 acts, it's 1 act with 2 possible outcomes that I'm going to include. Mutually exclusive events mean they have no elements in common. So, for example, if I'm looking at a spinner wheel, my sample space would be the values 0 to 9. And if I'm looking at A and B, and I'm looking to see if they have anything in common, they don't. So that if A occurs, then B cannot occur. So what does that actually mean? So that means that if I have 2 events happening and they can't happen simultaneously, then I'm going to add the probabilities of each event independently. So this is different. I'm not saying getting an ace or a queen. I'm saying I made 2 draws from my deck. One is an ace, one is a queen. So that's the difference here. The probability of the union events of those 2 mutually exclusive is the sum of those probabilities. I'm just adding them together. So let's look at what that actually looks like. 2 mutually exclusive events whose union is a sample space of complementary events, meaning when I add them together, I get some complementary values. And because the sample space of the spinner, or a subset of the spinner, if I'm looking at the probability that I have an outcome A, so 2 or 4, there's 2 ways to get a 2 or a 4 out of 6 total numbers. Therefore, the complementary event of A would be 4 out of 6, because that's, when I say complementary, that's saying that not A. So I want to say, what is the probability of not getting a 2 or a 4? Well, the probability of not getting a 2 or a 4 would mean that I would get a 1, 3, 5, or 6. Those are 4 items out of 6 total. So complementary is kind of like thought of as the not. And because it's a complementary event, we can find it with 1 minus my probability. So if I look back at this example, I have 2/6. If I do 1 minus 2/6, that would be 4/6. A lot of times we're doing that 1 minus process mentally, and we don't need to actually show it out. So let's look at some non-mutually exclusive events. Here I have E, and it's going to be the event of spinning an even number. So I can get a 2, a 14, or an 18. I'm going to spin again and have T be the event of getting a multiple of 7. So 7, 14, 21. So if I want the probability of E and T happening, then I'm going to have a little bit of a tricky problem, because look, 14 is in both groups. So it's not mutually exclusive because there is an overlap. I can get a 14 in both of these events. So I'm going to find the probability that something happens in event E. I'm going to add to that probability that event T happens, and I'm going to subtract the overlap. So there are 3 items in my group E. There are 3 things that I can go out of 8 total spinners, 3 over 8. Same thing with T. There are 3 total options out of 8, so that's where the 3 over 8 comes from. Minus the common group is 14. There's only one thing in common, so it's minus 1 over 8, and that gives you 5/8. So this is only when there's overlap happening. So we have a summary here. If I say P of the null set, that means it's impossible. If it's 1, it's going to be certain. If it's between 0 and 1, that's what we would expect the probability to be for anything. If A and B are events such that there's no overlap, so that would be like rolling an even number, then rolling an odd number. There's no overlap between even and odd. So that would be just adding the probabilities. If there is an overlap, you have to subtract the number of elements that overlap from that original probability. And if we have a complementary event, that would be the event of something not happening, we can find that from 1 minus. Let's look at just a few more examples. These are really important for the lab. A golf bag contains 2 red tees, 4 blue tees, and 5 white tees. What is the probability of the event R that we draw a red tee? Well, I have a total of 11 tees. I'm only doing one pull. I'm pulling one thing out. So 2 of those 11 are red, so the probability is 2 over 11. What are the probability of not drawing a red tee, meaning anything but red? Well, I have 11. If I take away those 2 red, that's going to give me 9 out of 11, so it's 9 over 11. What is the probability that a tee drawn at random is either red or blue? So can there be overlap? Can a shirt be red and blue? Well, no. So I'm just going to add the probability of getting a red shirt to the probability of getting a blue shirt, which would be 2 over 11 plus 4 over 11, which is 6 over 11. Here are a few other ways to view probability. Sometimes we look at it as the number of favorable outcomes over total number of outcomes, which is what I talked about with desired outcomes over total number of possibilities. A probability model is going to use geometric shapes to model an area. So when the area is modeled, it's used to determine the probabilities geometrically. So we're looking at geometry because it's shapes. Outcomes associated with the point are chosen at random in the region that represents sample space. This is often referred to as finding a geometric probability. That's really, really vague, right? So let's start designing some geometric models and see what they actually look like. So if I toss a fair coin, I'm going to say, here's my square, and it's a 50-50 shot. So I'm going to divide my square in half. So that would be a geometric model. So if I wanted heads, it would be 1 out of 2, and I'm modeling that with a shape. Do you see that? Rolling on a fair die, I would have 6 options. So I would want a 6-sided figure that I could divide into 6 equal portions. And then I would say this models it because if I get a 6, it's 1 out of 6. If I get a 2, it's 1 out of 6. So instead of representing that number, we're using a shape to represent it and create a model for it.